Hello everyone. Today we are going to talk about topology optimization of customized gear design for our computer-aided design course final project. The content for our project is problem statements, literature review, motivation and goals, methodology, MATLAB, Fusion 360, ANSYS optimizations, and their results, and finally conclusions and future work. For problem statements, gear components are crucial across industries like automotive, aerospace, and industrial machinery. Optimizing them improves energy efficiency, reduces weights, and boosts durability, enhancing system performance. However, traditional methods face challenges with complex geometries, resulting in exceed design cycles. To overcome these challenges, advanced techniques like topology optimization and generative design offer efficient solutions. They enable to exploration of innovative designs, improving performance while minimizing weight and enhancing efficiency. Integration of advanced simulation tools allows for comprehensive analysis and refinement of gear designs. By simulating various conditions, engineers can refine the designs to meet specific objectives like minimizing noise and maximizing durability. Additive manufacturing offers additional innovation opportunities. It enables the creation of customized, lightweight gear components, further enhancing system performance and efficiency. There is numerous number of examples in the literature. For example, Yokota Taguchi Gen conducted research on reducing gear weights and optimizing gear pair volume using methods like genetic algorithms. This study compared the effectiveness of optimization algorithms and examined the applicability of various methods to reach optimal solutions. And secondly, Saisani Ryo Wakaria developed an optimization methodology for polymer gear using multi-criteria optimization methods in gear design. This methodology considered factors such as tooth roots and flank stresses, temperature, wear, deformation, and also costs. Gear design optimization presents an interesting challenge in engineering, crucial for improving the efficiency and reliability of mechanical systems. Optimized gear designs promise significantly enhancement in energy efficiency, weight reduction, and overall system performance, driving our commitment to contribute to cutting-edge research in mechanical engineering. We aim to overcome current limitations with advanced optimization methods to revolutionize gear technology, making systems lighter, more efficient, and better suited to modern needs. Our main goal is to fine-tune design parameters to minimize compliance and optimization time simultaneously. Our project entails five main steps. Firstly, in MATLAB, we set the boundary conditions for our gear design and utilize the Ferrari and Sigmund 125 line code for our optimization. We analyze the optimization results to compare compliance and runtime. Then we repeat the optimization process for different parameters to determine the best variant. Subsequently, we apply Bezier surfaces to cover the optimized parts and generate STL file with our codes. For commercial products, we begin with creating a CAD model based on specific dimensions. Next, we optimize the gear design using topology optimization algorithms, adjusting material layout. We refine the optimization using Bezier surface to streamline further design manufacturing processes. Finally, we generate an STL file for final design.
Before initiating the topology optimization in MATLAB, it is necessary to produce a voxel mesh structure which suits for the required gear dimensions. After numerous experiments, it is found that analyzing 1/4 of a gear is time efficient while providing such homogeneous structures within the analysis boundaries, minimizing the compliance. After entering coherent boundary conditions to the shaft and outer diameter, it is time to find the optimum parameters for the customized gear design. At first, it is necessary to determine the minimum mesh size for experimentation and final mesh size for desired product. After running the simulation with same parameters but mesh size, it has been determined that 20 to 20 to 8 mesh size is the most suitable for experimentation, and 25 to 25 to 10 is the most suitable for final analysis. The second most important parameter for topology optimization is volume fraction. After numerous experiments, 0.2 volume fraction is determined to be used throughout. Further iterations has been made and the following parameters has been determined. Penalization constant is selected to be 3 because of the load paths remaining intact, and filter radius is selected as 1.5 because further values will make the analysis result more coarse and lesser values make the analysis much harder to understand. After trying other two filters, it has been found that both eta and beta is suitable for same values. However, filter 3 has given much clearer results with the same optimum parameters. Because all three filters gave their identical results, for the final analysis, all three filters with corresponding optimum parameters has been utilized. After the analysis completed, filter 3 has been selected as the best analysis result in terms of compliance and aesthetics reasons. After the customized gear, which has 29 teeth and a pitch diameter of 54 mm has been analyzed, Bezier surfaces has been drawn covering the analysis result. Smoothing the geometry while allowing necessary controllability across the geometry, bicubic Bezier surfaces has been selected as surface modeling approach. And the final geometry has been reached with a decrease of 70% in mass, while having 150 more surface area to dissipate heat.
In this part of the project, the worm gear we used in the senior design project was optimized in Fusion. The gears were made from brass and weighed half a kilo each. For this, we think that 3D ABS printing may be fit for these gears. In order not to take into account the pressure intensity, the shaft key keyway in the original mechanism was ignored. Our dimensions are diameter 60, depth 16, inner diameter 12 mm and 62 feet. Firstly, we started optimizing half and quarter gear. In the first test, volume fraction was selected as 0.6 and mesh was selected as 2% and optimization was performed. Even if we use different scales, general shape of scales are similar. Then, the same shapes were tested at 0.4 volume fraction. The clearest difference seen in this volume fraction is the difference in the arm thickness of the gears. Thirdly, volume fraction 0.2 was selected and optimization was performed by changing the mesh dimensions. According to the data obtained from this test, while gaps occurred in the structure with 2% mesh, these gaps were not observed in the structure with 1% mesh. As a result, it was predicted that the test with 1% mesh would be safer and allows more weight reduction. In the next step, the gears were examined by giving different mesh ratios in 0.2 volume fraction. In the left side, 1% mesh has smooth connection in the middle but 2% mesh has a gap in the middle. This shows that 2% mesh is not efficient like 1% mesh. It was realized that optimization made with a quarter-sized scale would be more efficient in the terms of weight reduction. Afterwards, the system continued to be optimized by reducing the volume fraction in the quarter-scale gear. Whenever volume fraction decreased, gear started to lose weight, but for torsion, we should stop it somewhere. In the last step, we were curious about comparing the quarter-scale gear and the 1/8 scale gear were compared at 0.1 volume fraction and 1% mesh. It has been noticed that the narrower the scale, the greater the torsional resistance of the created gear.
In ANSYS, firstly a spur gear created with using ANSYS Discovery and Space Clave. After the design process, Gear had imported the ANSYS workbench. In the workbench, created geometry used with static structural and structural optimization tools. With the help of given tools, calculations of structural analysis has been made, and different results of movements of geometry inspected. Coming to the results, the MATLAB model has a wide parameter network and high customization. These features cause workflow to be slow, prone to structural and design errors. The Fusion model has a high parameter range with ability to detail mesh angles in addition to mesh size. Since it is difficult to create the spaces inside the structure, it is not very suitable customization. As the meshes become denser, the workflow gets longer. Risks are more tolerable than MATLAB model. In the ANSYS model, the parameter range is high and customization is high. Unlike other models, structural analysis made on the mesh structure are more reliable than the other two programs. Workload takes a very long time due to detailed analysis. It responds to errors and tolerable level. For Fusion, the ease of the use and durability can be tested by printing and assembling the gear. Instead of ABS filament, different filaments can be used to find the filament that will minimize the cost. By changing the optimization scale of the gears, models with more branches and higher torsion resistance can be produced. In the ANSYS part, the gear observed by applying flow and heat transfer analysis for different operation environments. Different phase analysis can be obtained by changing mesh types.